let's look at the second example problem for meeting the middle. So this time we work with 4-sum instead of 3-sum. So this problem is called 4-sum 2 on LeetCode because there's another version of a 4-sum as well on LeetCode. So I chose to this second version because I think it has a very clean solution. So we are given 4 lists or arrays of integer values, and then we are asked to compute how many sort of ways to choose from this 4 list. So we choose one from A, one from B, one from C, and one from D. How many ways do we choose so that the sum is 0? So A, B, C, D, they all have lengths of n, where n is between n is at most 500, and also all the integers are in this range, so that adding 4 number will not overflow int, so we don't need to use a long for this. So here is an example. We have 4 size 2 arrays, so each of A, B, C, D have 2 numbers, and we need to decide how many ways that we choose their indices from the 4 so that the corresponding sum is 0. So the answer is 2. There are 2 ways to choose it. So we can choose this one here, this negative 2 here, this negative 1 here, and then 2 here. So that's 1, negative 2, negative 1, and then 2. So then the sum is 0. The second way is we pick 2 here, negative 1 here, negative 1 again here, and then 0. So 2 plus negative 1 plus negative 1 plus 0, that also gives us 0. So we are asked to find all such ways to make 0. And the possibilities is the total number of possibilities of the 4 indices is n to the 4. So that's quite big. So that will generally an algorithm with n to the 4 complexity when n is 500 is generally not acceptable in the context of either LeetCode or competitive programming. So we want to solve this problem in a way that's more efficient than n to the 4. I encourage you to pause the video and think about how you would solve it. Okay, so as we mentioned, brute force takes n to the 4. Let's first see how we can solve this in n to the n cube. So one way, as you may remember from the analysis of solving 2-sum nearest and 3-sum nearest, oftentimes sorting helps. So suppose we sort 2 of the arrays, then we can loop over the other 2 arrays, and there are n square combinations of them. And then for each of the combination, once we pick those 2 values, we are trying to find 2 numbers in these 2 other sorted arrays so that they sum up to negative of the sum of the 2 first values, so that the total sum up to 0. So that can be solved using 2 pointers. So this is slightly different from 2 pointers on in a single array, because the 2 pointer actually point to 2 different arrays. When we start, one point to the beginning of the first array, the other point to the end of the second array, and both of them are sorted. But the exact argument apply, we compute their sum. If it's less, we move the left pointer to the first array, and if it's too big, then we move the right pointer to the we move the right pointer in the second array. So that will give us a complexity of n cube. Now, can we do better? It turns out that we can. So we can solve the problem using complexity n squared, but this requires us to use some extra memory. So the n cube solution actually doesn't use any, only use constant amount of extra memory. We're just sorting the 2 arrays, and then we don't need to allocate new arrays. But to solve this in n squared, we have to use extra memory. In fact, we need to use n squared extra memory. And what we do is we take two array and then we compute all possible sums of these two array, and then we store this result. So then this enables us to solve the problem efficiently, and this is the essence of meet in the middle. That is, we sort of have a four arrays. We really need to consider all combination of first two and all combination of the second array. But by computing all combination of first two array and then store it, then the complexity become just the square root of n fourth. So I'm going to yeah. So here's the code. So it turns out actually the code is fairly short. So we are given four arrays A, B, C, D, and this time this code is in Java. So I use one hash map, which stores for every sum how many times it occurs. So I will iterate through all combinations of A and B, so for every x in A and every y in B, I will store x plus y in this hash map, and if it already exists, we'll increment the counter. So this is a syntax for doing that. So this is hash map support this map support this function of merge. So this starts from Java 8. So Java 7 doesn't have it, but Java 8, starting with Java 8, we have this feature. So make the code sort of shorter, and then we iterate through all combination of C, all value in C and all value in D, and then in this case we are trying to see whether the hash map include the value negative x plus y, because if it does, then we have find one way of getting 0. So we get this the number of times negative x plus y appears. If it doesn't appear, we will just use 0. So remember, the question asks us to count how many of this sort of four tuple of indices so that the sum is 0. So this basically looks for every possible combination of element in C and D, how many times we can find a pair of indices in A and B, so that these four numbers together sum up to 0. So we just keep adding this to the answer. And that's it for this problem. So now we can sort of take a step back and look at the problem we have considered. So we considered the 2-sum, 3-sum, and 4-sum, and actually two different variants. One is the exact sum. So we are given a target. We are trying to find things that exactly match. Sometimes we are asked to find the indices. Sometimes we are asked to count how many times. They are more or less equivalent. And then the other version is the nearest sum. So we are given a target, but it may be that there's no instances that will sum up to this target. We want to find things that are closest. So this is harder than exact sum. And let's look at the complexity of the best algorithm that we know at this point. For 2-sum exact sum, we can use the hash set. So this will use on time and also on extra memory for the hash set, or we can use the method that's sort of also used for near sum, which is we sort the array and then we use 2 pointers. So this algorithm can solve both exact sum and the nearest sum in n log n time, but there's only 01 extra memories. And for 3-sum, the best method for 3-sum we know have the same complexity as the nearest sum. So for 3-sum, the best approach is we sort 2 array and then we iterate through the third array. For each element, we will use 2 pointer over the 2 sorted array to see whether to find exact sum or near sum. This 2 pointer method can work. So we have n square time because the iterate over the third, there's n choices, and the 2 pointer also take on time. But we have a O1 constant amount of extra memory. And the best algorithm for exact 3-sum is the same as that one. So for 4-sum, For exact sum, we can use the algorithm we just the code showing on the previous slide. So we use n square memory. In that case, we use a hash map, and the algorithm also take n square time. If we are trying to solve near sum using a hash map, doesn't work. We need to use a sorted array. So in that case, one way to do it is we compute all sum of two array, and then we store that in a size n square array, and then we sort it, and then we do the same for the other two arrays. So we have one array storing all possible sum from A and B, and the other array storing all possible sum from C and D. We sort both, and then we can use two pointer to solve whether near sum or exact sum. So the complexity here is n square log n, because we actually need to sort an array of n square elements, and the actual memory is O(n) squared. So one of the problem in this week's problem set is a 5 sum. So you can see how to do that, and you can, I guess, based on the pattern we see here, I don't know whether you see the pattern and you can guess the complexity of 5 sum, and similarly complexity of 6 sum. So essentially, this algorithm here for 4 sum will also work for 6 sum or 8 sum. So essentially, if it's an even number k sum, then the complexity is square root or n to the power of k over 2. And for 5 sum, it's the complexity, the worst case time complexity, is the same as that of 6 sum, but I think it may need you can do it with a bit less memory. You don't have to use n square will suffice. I'm not totally sure whether you can do it with just the linear time of actual memory. I think it's unlikely. Okay.